Okay, welcome back. Good morning, guys. Hope you're all doing well. And we just have a few minutes, I guess, 2 minutes until we get started. Feel free to tap into the chat anytime. Good morning, Nina. Ryan, welcome back. Hi, Claire. Oh, that's great. Good to hear that, Ryan. Yeah. How are you feeling? Hopefully not too bad. For me, I was just a little fatigued for just about a day, but no real serious issues with it. Hi there, Grant, Ryan, Claire. Okay, that'll be great, Claire. Yeah, I'll be here. So anytime, anybody who wants to at this point, at least from my perspective, now that I'm fully vaccinated, I trust that you're going to take your precautions and do what you think is best. You don't have to attend, but if you want to, we do have a big classroom. There's plenty of space. So we could definitely fit a couple of people in here if anyone wanted to try it. I wonder, would that be your first ever time coming to class in college? It's crazy to think about that just because of how much of a big part of my college experience was just being in the rooms. And so anyway, though, we'll be back to normal soon. Good to see all you guys here. I see you all in the chat. Eloise, Dimitri, Steven, Nicole, Finn, Nicole, Jianyan. Okay, guys, so it's 9 a.m. Thanks again for being here, as usual. Today, we have another important meeting because we're going to make a move to another new topic in the semester. So we've gone through some important lectures on epistemology now, just recently, and that followed our discussions of ethics, which followed our discussions of the philosophy of religion earlier in the semester. And we still do have a couple of more important big areas of philosophy to study. Today, what we're going to do is start talking about another important subject area of philosophy, which they call metaphysics. And philosophy, religion, ethics, epistemology. Now we examine another branch, which is called metaphysics. So this is the word I'm talking about, metaphysics. Now, in the original usage by the ancient Greek philosopher Aristotle, he wrote a book called Metaphysics, and he just meant something that goes beyond the study of physics. But over the generations, it's kind of taken on a slightly different meaning, and it just has to do with like a deep exploration of reality and the nature of the things that exist. So So when we have kind of like just a really focused, penetrating investigation of the nature of reality itself, or what things exist in reality, that's when we're doing metaphysics. And metaphysical inquiry can take any number of different topics as its starting point. Sometimes within metaphysics, people talk about the question of human free will. Do we have free will, or are we just objects kind of governed by the laws of nature, caught up in this physical system, and therefore our actions are actually determined? Or another question could be, how is it that an object maintains its identity across time if it's losing some of its physical parts? As you guys probably know, like a human being is the same human being today that they were when they were a little baby. But if you compare the size, shape, etc. of the baby with the adult, is much different. And the cells in your body are completely recycled every, I don't know, you've heard this fact, I'm sure somewhere, like 7 years or something. So each physical cell in your body today has nothing to do with the cellular composition of your body 10 years ago, but you're the same person. How does that happen? So some people talk about identity and persistence across time for objects or for persons. What is the nature of persistence across time? What is free will? What is the nature of numbers? Are there real such things as numbers, or are they just abstractions from physical objects? Okay, well, I'm just giving you a sort of sampling of topics that people consider in metaphysics. But the one topic in metaphysics that I've chosen to focus on for us this semester is the philosophy of time. What is time? So we're going to really focus on time for a couple of weeks here, and that's our now topic. So metaphysics, but under this heading, it's really, for us anyway, metaphysics of time. So the thing about reality that we're trying to investigate and explore what it's all about, what the nature of it is time. What is time? What is the nature of time? And asking questions about how to analyze and understand the concept of time is very, very deep, puzzling, and almost trippy and bizarre. Well, when it comes to time, obviously we're all very familiar with time. We live our lives according to the clock. You guys know that the reason that you're watching this lecture right now is because it's timed at, the 9 a.m. hour of Monday, Wednesday, Friday. So each part of your day and schedule goes in accordance to the passage of time. You're aware of the passage of time. You're aware of how much time has passed in your life, how much time you perhaps have left to live, how much time remains within a given interval, like when you're doing tasks or accomplishing duties. So time is just a fundamental aspect of our lives and of reality. But the thing about it is we kind of are so familiar with it in our everyday life and experience that we usually don't take a step back to try and ask questions like, what is it though? And how could we understand it in a basic sense? And you'll come to see that it's actually quite difficult to provide any in-depth analysis of time once we go beneath the surface level of depth. But we'll try to get to that better analysis and that better understanding as much as we can. And we'll try and take some help from the great scientist and philosopher Albert Einstein. So that's the author for today, Einstein. And let's show his dates of life. So Albert Einstein, he lived from 1879 until 1955. And we're reading a piece taken out of a larger work of his from the year 1916. So this book that he wrote in 1916 is like a popular, it's a publication that's directed at a more wide audience than just, theoretical physicists, mathematicians, etc. The work of Einstein, his original papers, on the electrodynamics of moving bodies, which contained the general and special theory of relativity from 1906, those works are very, very technical and intimidating, so it's hard for a layperson to understand them. Einstein knew that, and since he wanted to have more broad social understanding of his work, he wrote this book in 1916 that's just called Relativity. It's a great book. He tries his best to bring these heady ideas down to earth for the everyday person to understand. And so Relativity from 1916, that's where we find the selection that's been put in our anthology. And Einstein basically tries in this piece to explain some fundamental aspects of the theory of relativity. Now, in our textbook, they've extracted a snippet from the big book Relativity, and they've retitled it. So I just want you guys to know that this is the original book from which the section has been taken for our anthology. But in the anthology, when you look in it, you're going to see that it has this new title. They simply retitled it Time and the Relativity of Simultaneity. So Einstein, Time and the Relativity of Simultaneity, from his book Relativity in 1916. And I mean, Einstein, you guys I'm sure have heard his name. This is one person who's definitely a household name when it comes to, the whole world and especially the West. His groundbreaking theories about space and time really revolutionized our modern day understanding of those concepts. And so impressive because he published these these Nobel Prize winning papers on physics when he was in his early 20s, working as a patent clerk at a patent office in Germany. So very, very impressive resume. As you guys, I'm sure, understand, Einstein is sometimes, I argue, like the kind of cultural meme of the genius scientist. You know, like when you have a thought in your head of the stereotypical image of like a true genius, you think of the crazy hair and mustachioed face of the rumpled sort of what do they call it, shabby academic look of Einstein. So a lot of people have seen him and they know his figure and his persona, but not everybody understands the basics even of his ideas and why they're so revolutionary and important. So we're going to try our best to at least scratch through the surface and get into the ideas of Einstein. So I'll just say this as a precursor to the more detailed lecture to follow, that he took us away from the older Newtonian conception of space and time. And that's why he's so famous. He revolutionized the modern day understanding of time and space. So prior to him, the paradigm that was dominant was Newton's laws of physics. And according to Newton, space and time were completely independent of each other, meaning that no matter how fast or slow an object moves through space in terms of its speed, that would have absolutely no effect at all on the rate of the passage of time. So it was thought that time just moves at a constant, steady rate, and that rate is absolute and unchangeable, and nothing that happens with respect to the motion of objects relative to one another could possibly affect or alter the constant and steady passage of time. But what Einstein showed is that this is not actually true. Space and time are not independent. In fact, they're interwoven into one common structure, which is called space-time. And according to the space-time concept, the motion of objects through space and their velocity relative to other objects does in fact affect and change the way that time passes for that object relative to others that are also in space. So we're going to try and show this relativistic conception of space-time. And once we get into it and once you kind of grasp some of those basics, I think you'll see that it actually has very far-reaching and even puzzling, trippy implications for our understanding of the universe and ourselves as objects within the universe. So let's go ahead and try our best to get started on this discussion of Einstein's theory of relativity. And as I see all you guys here in the chat, I definitely appreciate your attendance, and so thanks for being here as usual. Okay, so let's begin his discussion. He says this. He starts off with a theoretical example, like a thought experiment. So here is Einstein's hypothetical scenario for you. He says, consider that there are two lightning strikes that occur at two separate positions along a railway embankment. So now that we have the title information, I'm going to clear this away. Okay, so let's say that this here line stands for, I got to make a better line, sorry for that. Let us say that this perfectly horizontal line is a railway track, basically. So like a train or whatever could move along this track. I want you to say that two lightning strikes happen at two positions along the railway. So here's one of the lightning strikes, and here's another one of the lightning strikes. Let's mark them on the railway embankment with the two marks A and B. So position A is the position where this lightning strike occurs, and position B of the railway is where the other one happens to the right. Okay, now, I want you to make what is a deceptively simple assumption about the lightning strikes here. Let's just assume that they happen simultaneously. Assume, you heard me, that the two lightning strikes that strike the railway happened simultaneously. Now, question from Einstein to you. What does that mean, though? Can you tell me what it means, in other words, for the two events to be simultaneous events? And the thing is, and Einstein mentions this, it's not so easy to actually define the concept of simultaneous, because go ahead and try to do it. Any attempt to do it essentially becomes circular. You start grasping for a word or words to explain simultaneity, and you end up saying something like, they happen at the same time. But to say that the things happen at the same time is just to say that they are simultaneous with each other. So is there any way that you can define simultaneous without having a circular definition that just loops back and says simultaneous means simultaneous? Any attempt that you could make? What do you think it would be to say that two things happen simultaneously? And the only sort of rule is you're not allowed to say anything that is elliptical for they happened at the same time. So can you do that? Just try. I don't know. Give an attempt, if you will. You think of the word simultaneous. I'm sure you understand its meaning, or you kind of understand it. Can you tell me what it means for the two events to be simultaneous? And it's okay if it's hard, and it's okay if you feel like not equipped to say so, because you're in good company. Einstein, the great genius, says this is not so easy to define as it might sound at first. But any takers, any thoughts on this? Any good, bad, middle attempts to give such an explanation of simultaneous? Okay, so Ellie, there's no difference in time between the two events. Well, that would, I guess, be trying to state it in the negative rather than in the affirmative. They happen at the same time, so this would be like the negation of that. It is not the case that they happen at different times. But saying that it's not the case that they happen at different times is logically equivalent to saying that the two events do happen at one and the same time. Connor, you say done at the same occurrence. I like that. We're trying to get away from saying same time and talking about the events occurring. But I suppose that in a way, if you think about the two things occurring in the same moment, that sort of just means simultaneous yet again. Occur in parallel. I like this also, Ryan, but maybe parallel, as much as it sounds differently from same time of two events, is kind of, if you really break it down, getting to that same point. So anyway, let me read from the Einstein for a bit, and you can see why he thinks this is not so easy to say, and you'll hear it from him. Okay, so to begin, he says, lightning has struck the rails on a railway embankment at two places, A and B, distant from each other. I make the additional assertion that these two lightning flashes occur simultaneously. Now, if I ask you whether there is meaning in that statement, you will answer yes. But if I approach you with a request to explain to me the meaning more precisely, you will find after some consideration that the answer to this question is not as easy as it appears at first sight. So after some time, perhaps the following answer would come to you. And he imagines someone saying this back to him. He imagines someone, let me preface it with my own way of putting it. He says that somebody might kind of throw up their hands and say, look, do I really need to explain what it means, though? Can't we all just agree that it's already understood? When people say the word, nobody shrugs their shoulders like, excuse me, what do you mean? So isn't it just clear enough from our everyday life and usage? So I don't need to give you your detailed explanation, Einstein. He imagines someone saying that, but he says that's not going to work. So let me read it now. He says, after some time, this might come to you. Quote, the meaning of the statement is clear by itself, and it needs no further explanation. Now, if I was required, it would require some consideration if I was commissioned to determine by observation whether in the actual case the two events took place simultaneously or not. And Einstein answers, I cannot be satisfied with this answer for the following reason. And what he's going to say next is, as a scientist, we cannot have a concept that is vague or not clearly defined. In science, he thinks that for a concept to have any kind of concrete meaning, there must be a way of determining by means of a physical experiment whether the definition can be applied to the case or not. So he says, what we really need is a method by which we can test if the two lightning strikes are simultaneous or not. So he thinks to understand what it means for them to be simultaneous, we would have to give the parameters for conducting a physical test of simultaneity. And he says if we cannot come up with the means by which to design such a test, then we might be using the word simultaneous with no meaning at all. Maybe we're using the word, but at the end of the day, it's actually an undefined concept. So he says, I can't be satisfied with that answer for the following reason. Suppose that as a result of ingenious considerations, an able meteorologist was to discover that the lightning must always strike the places A and B simultaneously. Then we would be faced with the task of testing whether or not this theoretical result conforms to the reality. We encounter the same difficulty with all physical statements in which the concept simultaneous plays a part. And here's kind of the key quote I was mentioning. The concept does not exist for the physicist until he has the possibility of discovering whether or not it is fulfilled in an actual case. We thus require a definition of simultaneity such that this definition supplies us with the method by means of which, in the present case, he can decide by experiment whether or not both the lightning strikes occur simultaneously. As long as this requirement is not satisfied, I allow myself to be deceived as a physicist, and of course the same even if I'm not a physicist, when I imagine that I'm able to attach a meaning to the statement of simultaneity. And he says, I would ask the reader, don't go any farther from this. Do not proceed any farther until you're fully convinced on this point. Okay, so what he says there is, to anybody who thinks The concept of simultaneous, it's not important to define it with any precision because it's something that's kind of intuitively understood in the mind. He says that won't do because if we don't have the ability to actually design some experiment which could verify that the events are simultaneous, then we may be using a word which actually has no clear definition and therefore it's meaningless. So let's try and figure out how to test this proposition that the two events are simultaneous. So what is the test? What is the test for simultaneity? Einstein says, okay, I got you. I'll tell you what the test is. So here's the idea that he provides to the reader to test the question of simultaneity. And good morning, Elif. Good to see you too. So he says this, let's measure the distance from the two positions on the railway embankment. Okay, so let's take the distance from A to B and place an observer right at the midpoint in between these two. Okay, so like A to B, we can consider that to be like a line segment, the line segment AB. That's the line segment which initiates from this point and terminates at that point on the other side. Now, with every line segment, if you guys know your geometry, there's always a midpoint. That's the point which bisects the line and evenly divides it into two halves. So let's say this is the midpoint M in between the two positions A, B. Let us place an observer here at the midpoint M. So this is a person that's observing the two positions A, B from his standpoint at M. Now, here's the thing. This person is equally distant now from A and from B. That's why he's at the midpoint. He's equally far from the two events. One thing that Einstein says next is we have to make sure that this person who's at M is standing back far enough from the railway so that he can see the 2 points A, B in one field of vision. It has to be such that he doesn't have to like shift his gaze from right to left to see A and then B, or vice versa. Do you understand that? Why do you think it's important for him to be far back enough to see the two events in one field of vision? Because this guy's going to be the one that's going to monitor whether the two things happen at the same time, but he could not possibly verify whether they happen at the same time if he couldn't what? Can you help me with that last point? Anyone can take this up. Why is it so important in the setup of the test for Mr. Observer to be able to see in one and the same frame the 2 points, A and B? Because remember, his task is to assess whether they're simultaneous. So why should it be that he has to be able to see them 2 points in one frame of vision? Why is it so critical that he does not have to, let's say, shift his gaze back and forth because he's too close to one of them to see them both at the same, in the same visual perception? What do you think? Please let me know. Yeah, because to try to see if they're simultaneous, I guess so, Alex. I mean, in a way, that's summarizing the same thing I said. But if he had to cast his gaze from right to left, you see, well, it's not about it being so fast, Eric. Also, no. Okay, I'm trying to talk to you about why he has to be able to see the 2 points in one field of vision. If he's close up to A, right? So like he's so close to A that he can't see B at the same time, then in that physical position, he's not in a position to judge whether they're simultaneous. Because suppose that he looks at A and he sees a lightning flash there. Then he quickly shifts his look over to where the position B is, and he sees a lightning flashing there. Would that be a way of determining if they're simultaneous? No, because it takes a moment of time, doesn't it, for you to avert your gaze from one point to another. And so in the time interval that it takes from him to move his face from A to B, it could have been that B started happening subsequent to the event A. So you actually have to be able to see the 2 parts of space, obviously, to be able to make any judgment about whether they're simultaneous or not. Is this clear? Because I didn't see many people taking it up, but I think it's somewhat clear, right? You have to be able to see the 2 things to be able to tell whether they're simultaneous. If you're looking at one and then afterwards, subsequent, like in a sequence, you look at the other one, you can't possibly check to see if they're simultaneous or not. So he says they got to be far back enough. And if they're not far back enough, then let's make sure that they have some kind of 90-degree mirrors at angles so that the mirrors can supply them with the means to see both events in one field of vision. Okay? So now, with that in place, if we have our observer well positioned to see the 2 points, A, B, and if he then sees the 2 things happening at the same time, in the same visual perception from his standpoint at M, then in that case, we would claim that the 2 events were simultaneous, but we have to add a little bit more information here. Okay? Now, how is it that vision works, guys? Why is it that when you open your eyes, you can see things? Like literally get down into the details. How does an eye see? What is the mechanism by which your eye takes in visual information from the environment? So what's the carrier of the visual image to your eye? Let me know this, and then we can go from there. How is it that vision works? Is it magic? How can you see this screen that you're looking at? It does reflect light. Okay, so the eye collects light rays that are reflected off the surface of whatever object in space that you're looking at. So right now, as you see the screen, there are light rays bouncing off of the screen, fired at your retina, and then that visual information gets processed by the brain and you see the image. It happens very quickly, but that's how it works. So why is it, of course, that when you close your eyes, you don't see anything? Well, that's clear, I hope. It is because with the eyelids closed, you are blocking incoming light rays from being able to hit the eye, and therefore that's why the vision field is black with your eyes closed. Okay, so with this guy at the distance position from A to B at point M, he's equally far from the two events. Now, if we stipulate that the speed of light is constant and fixed, so that it is the same velocity from A to M as the velocity of light from B to M, then in that case, this will verify simultaneity. But we have to make that assumption of the fixed speed of light. Okay, so as he's standing here at M, the light signal from A reaches the perceiver, the light signal from B reaches the perceiver. We have to assume that the speed of light is constant, and it is not faster from A to B than it is that it is not faster from A to M than it is from B to M. Let me try and make that clear to you. Why? Okay, so if he receives these two light signals at the same time, but they're traveling at different velocities, then we could not infer that they departed from their origin points at the same time. If, on the other hand, light moves at a constant speed, then we can infer, based on his position, when they arrive at him at the same time, that they were emitted at the same time. Because look, these two things are fixed. Is the distance from A to M the same distance as the distance from B to M? Yes, it is. That's why we designated the midpoint M, because it's equidistant from A and B. So these two line segments, B to M and A to M, are of equal length. And if the light is traveling at that equal distance at the same velocity, and it reaches and converges on a common endpoint, M, at the same moment, then that would mean that they departed from their origin points A and B at the same time. But if they were moving at different velocities, and even if they arrived at M at the same time, we would not be able to establish that they departed at the same time. Let me give you an example to help explain that point. Let's suppose that A and B are not lightning strikes or rays of light, but rather runners that are running like a race. And the finish line is where this guy is standing at M. So B is trying to get to M, and so is A. Now suppose that A is a much faster runner than B, and that A is twice as fast as B is, okay? So now, I want you to imagine that A and B reach the finish line at the same exact time, but A is twice as fast as B. If A is twice as fast as B, but they reach the finish line at the same time, then my question for you is this: did they depart at the same time? Or if they didn't, then who left earlier and who left later? When A is twice as fast of a runner as B is, but they arrive to the finish line simultaneously, then who left first? Let me know that. I'll just keep repeating the point as you think and type. A is twice as fast as B at running. They have an equal distance to cover to reach the finish line, and they arrive at the finish line at the same time. So in that case, A left later. Yes, if A is twice as fast, let me correct you there, Eric. If A is twice as fast, then for him to arrive to the finish line at the same time as B, he had to give B a head start. So think of it like this. B's slower, A's twice as fast. So A is like, go ahead, you go. And he's going, and he gets halfway there. Then he leaves, and because he's twice as fast, they meet at the finish line at the same time. So we have to assume then that light is not like these two different variable speed runners. Otherwise, the common receipt of the light signals at M would not imply that they departed their origin points at the same time. But if we do stipulate that light is constant and fixed, then we get the desired result. that in case they have arrived at the observer at the same time points, then they must have derived from their origin points at the same time, since they have traveled an equal distance, moving at the same speed, and have arrived at the same terminal point simultaneously. Okay, so that's what he says. This is the method then by which we could test for simultaneity. Place an observer in such a position that the light signals emitted from the two events reach their visual system at the same time. And in that case, relative to this observer, for whom the light signals reach them at the same time, we can say that the two events relative to this person are simultaneous. Let me read then the words of Einstein, and you can hear his way of putting the same point. He says, after thinking the matter over for some time, you then offer the following suggestion with which to test simultaneity. By measuring along the rails, the connecting line AB should be measured up, and an observer placed at the midpoint M of the distance AB. This observer should be supplied with an arrangement which allows him visually to observe both places A and B in the same visual field. Now, if the observer perceives the two flashes of lightning at the same time from this position, then they are simultaneous relative to him. And he says, I'm pleased with this suggestion, but for all that, I can't regard the matter as quite settled because I feel constrained to raise the following objection. Your definition would be correct if only I knew that the light by means of which the observer at M perceives the lightning flashes travels along the length A to M with the same velocity as along the length B to M. And then he just says, I simply will stipulate this in order to arrive at my desired definition of simultaneity. So now, given this analysis, we are able to define what it is for any two events to be simultaneous. Relative to a given observer, two events are simultaneous if the light signals emitted from the events reach the person's visual system at the same time. And so how is it then that clocks work? What we're able to do with clocks is just coordinate the clocks so that they're all kind of moving roughly in unison. And then we can simply coordinate events in space with the pointer hands or digital clock face of the clock. So like in a classroom, when it says attend class, assume that we're having physical classes, and it says be in class at 9 a.m. on Monday, Wednesday, Friday. When you arrive, let's say on a Monday at 9 a.m., what you're doing is making two things be simultaneous, two events. The pointer indication of the clock showing 9 on the clock face, and then you taking the seat in the classroom. If you observe these two things happening at once, like visually, then they're simultaneous relative to you. But the trippy thing about this, we're only starting to scratch the surface of how weird this really is, because now we're going to part 2. What you're going to learn now is that based on this analysis of simultaneity, simultaneity is not absolute and it is relative. And that is just very strange, and it leads to a whole bunch of puzzling results. So let me try and show you the relativity aspect of this discussion now. And for us to do that, we have to add some features to the example that you see here on the board. So we're going to add a secondary observer to the scene. Now, suppose that we have a train now, which is actually traveling along the railway embankment, like so. And it's moving from left to right along the railway with the constant velocity v. Okay? And inside of the train, there is an observer who's also just riding along and shares the velocity of the train. Now, each observer, given their state of motion, can be described as having a different frame of reference. So one frame of reference is the motionless observer who's standing still at point M. Another frame of reference is the reference frame experienced by the moving observer who's traveling with the velocity v of the train. So the observer who's in the train regards all events relative to the moving train, and the observer who's on the embankment motionless observes all events relative to his motionless stationary position there at M. Now, I want you to imagine that this observer who's moving with the train is going to surpass the midpoint in between A and B. And since this is the midpoint as seen from his frame of reference, we're going to designate it with the label M prime. Now, M and M prime are obviously aligned because they fall on the same plane, which bisects A and B. Okay? So now I want you to ask this question, guys. As A travels, sorry, not A, the second observer, the guy in the train, as he travels with his constant velocity v, he's going to align with the midpoint here
that the other observer is positioned at from his standpoint. Now, I want you to suppose the following, that as this guy in the train strikes the midpoint along his route, that it is at that exact moment when this guy conducts his observation of A and B and sees them to be simultaneous relative to his standpoint. But we have another observer up here that's moving with the velocity of the train, and at that split second that this guy does his observation, they're in parallel. This guy's at M prime, and he is at M. So I kind of want you to, if you can think about it visually, as like a video playing through. And if you were to hit the pause button at the exact right moment, you would have these two characters aligned along that plane described by the midpoint M. The guy in the train would be at M prime, and the guy on the embankment would be at M. So let me ask you this. When we unpause the video, as it were, from that like frame, will the guy in the train remain at the midpoint? Yes or no? We know that the guy standing at the embankment will remain in his position at the midpoint. But if we allow this video playthrough of the sequence of events to continue from the paused frame where they're aligned, will the guy on the train remain at the midpoint, or will he move? Will he remain at the midpoint, or will he move? The guy in the train, if we unpause the hypothetical video that I'm trying to get you to mentally visualize, he will move, Dimitri, yes, because he's got velocity of the train. So it's not like the train breaks down when it hits the midpoint. It's not a wall, it's just an imaginary midpoint. So he continues to pursue the pathway of the train on its path to the right. So here's the question, guys. The guy that was at M saw the two events happening simultaneously because the two light signals reached him at the same time where he's standing. But when we add the second observer to the scenario, and he passes through the midpoint and traverses it at the exact split moment when this guy conducts his observation, tell me, will the second observer see the two events A and B happening at the same time, or will he see them happening out of sequence at different times? So we already said that relative to the first observer, he sees them happening at once. Will the second observer who passes through the midpoint with velocity v, will he see them happening simultaneously, yes or no? The second observer who's got the velocity of the train, who is going to continue moving to the right as the first observer conducts their observation, will the second observer see the events happening at the same time, or will he see them happening at different times? Well, Ellie, you say no. Let's phrase your answer in terms of, will the two events be seen as happening at the same time or not at the same time to the second observer? And Alex, you're saying he will see B first. Yes, he will definitely see B first. So that is the correct answer, Alex. Let me see if anyone can tell us why. Why is it that for the second observer, the two events do not appear to happen at the same time? In his case, it is B that he perceives happening first, and only a moment later will he see A. Why is it that the second observer sees B before A, given his state of travel and his velocity relative to the other observer? Tell me this. Alex, you seem to have the right intuition, so maybe you can explain, or if others have the same sense, you can tell me why it is that he will see B occur prior to A, the second observer who's traveling towards B and away from A. Why is it that he will see B first and not both at the same time? Dimitri, you say he's not far enough away to have, no, that's not it at all. So sorry, let me make sure you understand. It's not just something where like, oh, it's behind him now. He's got mirrors, okay? So whatever the case is with these two events, he's gonna see them in the correct order. It's not like he's just obscured from the visual of the one that's back behind him, no. Ellie, because he's moving towards B immediately after it happens, so it'll be closer to him, and that is right. Alex, he is facing and heading towards B, and A is behind him. Also, that's correct. So here's the deal. Light signals have to reach your eye for you to see the thing that is emitting the light, or that the light is reflected off of. So with respect to the first observer, because he stands still, the two light signals are reaching him the same moment. They're traveling equal distance at the same velocity, reaching a stationary observer at a midpoint at the same time. But in the case of the second observer, look, as he bypasses the midpoint at the moment that this guy does his observation of simultaneity, he continues traveling over to the right with constant velocity v. So he's running away from the light source emitted by A, and running up closer to the light source emitted by B. So unlike the first observer, he's not posed equidistant between the two events that are trying to find his visual system. He's farther from the light source of A, closer to the light source of B, and therefore, since they're moving at the same velocity, since light moves at a constant speed, they cannot possibly reach his eye at the same time. Since there's an asymmetrical distance, A has to travel farther to reach him, B has less distance to travel to meet his eye, and therefore B inevitably is going to be perceived first and then A subsequent to that afterwards. So how weird is this? The same two events, A and B, are being seen in a different order by two different observers. One of them, motionless, sees them occur at once, simultaneously. Another one, moving in the path towards B away from A with velocity V, sees B happening first due to his closer approach towards it and his state of motion relative to the other observer. Now, you might hear this, and I don't want you to misunderstand it. So let me ask a question that's a trick question, and I'm just going to tell you that. Which of these two observers is correct? Are the two events simultaneous, or are they not simultaneous? What is the answer? I'm telling you it's a trick question, so think about your answer. Are they simultaneous or not? Point blank, the lightning strikes. In this situation, are they simultaneous or not? I know I say it's a trick question, but try to give your tricky answer. Are they simultaneous? Yes or no? You have the ability to give the answer based on the information. So are they simultaneous or not? Ryan, you say you think they are simultaneous, but depending on where you are, it may seem like they occur at different times. I knew that someone would say this, but I'm sorry, no. That's not the answer. So what do you think is the answer? Alex, you say it depends on how you are perceiving them. I think this is better. The right answer is simply this: both. It's relative. There's no objective fact about it. They're simultaneous relative to the motionless observer. They're not simultaneous relative to the other observer. Now, you might be thinking, as I suppose Ryan was thinking, but isn't there an objective fact here? They're really simultaneous, and the other guy's just seeing like an illusion that's been created by the fact that he's in motion. But that's not true. Everything's in motion at all times. There's no objective standpoint from which to observe any two events in the whole universe, because you may think you're motionless right now, but you're riding along on the surface of the Earth, which is traveling in the solar system at a very high rate of speed. So you're only relatively motionless to other things that have a different state of motion than you. So it's not as if our observer who's positioned on the train is not seeing like the real perspective, and the other guy, because he's standing on the embankment, is seeing the so-called real perspective. Each have equally valid claim to have seen the events in whatever order. So there's no fact about whether they're simultaneous or not. And once you really can process and understand that, it just becomes so weird and trippy. It has bizarre implications that stretch across the board when it comes to the way you would understand yourself and our position with respect to the universe. Let me make it even weirder for you now, okay? Suppose that we have a third observer, and they're on a separate train that's moving in the opposite direction. So this train is going in the opposite direction of travel from B towards A. We have an observer positioned on this train, and let's suppose that as they go in their direction, they surpass the midpoint as seen from their frame of reference, and let's call it M double prime. Now, suppose that as these two trains are going in opposite directions, not along the same track, they're not going to smash into each other, but as they do that, there's a brief moment where they're all aligned, again with the motionless observer. And it is at that moment of alignment that the motionless observer perceives the two events happening simultaneously, given his equal distance from the two events and his motionless state. But as I told you before, this observer will not see them happening simultaneously, given his constant velocity and direction of travel towards B and away from A. So now consider the third observer who's on the upper train. If they're going in the opposite direction, towards A, away from B, then what will be the order of events perceived by this third observer? They will see which thing happened first before what? What's the sequence of events to observer number 3? For this guy, simultaneous. For the other guy, it's first B, then A. And for the top individual, it's what order? Just let me know the order of events in terms of the two lightning strikes from the second observer's perspective. since you've already seen how it works in the other case, this should be quite easy. It's the same, but just in the opposite direction of travel. So what is the order of events? Yes, in the second case, or the second train traveler, he sees A before B, because as he's moving closer to A and away from B, there's a longer direction of travel for B to go in order to reach his visual system. They don't meet at the middle. B has to run up ahead to catch him, and he's closing the gap between himself and A. So now look at A and B, the two lightning strikes. We started off by just asking what it means for the two things to be simultaneous, but now we have a very bizarre set of facts to consider. On one account, the two events are simultaneous. On another observer's account, it is first B and then A. And on another observer's account, it is first A and then B. Now, which is correct? And now the answer is all of them. Relative to each observer, that is the given order of events. But that is so strange because if you think about it, it means that there's no objective fact about the order of the two events. So we can't say, like, objectively, they are simultaneous, or no, it is A that happens first, or no, that is B that happens first. And when you understand this concept, it has this really wild implication that all the events of space-time are equally real, and the order in which they appear to happen is only a consequence of your state of motion relative to other observers in the universe. So, like, you think of things that have happened yesterday as happening before the things that have happened today. But there's another possible position from which to observe the events in space-time that would have the events reversed in order. And so it's so strange. What that means is that the events of future time relative to you right now are already existing events relative to some other frame of reference. And that starts to really spin out into wondering whether or not we even have free will. Because if this Einsteinian space-time conception is true, then every event of space-time, completely inclusive of the past, present, and future, are all equally real, even right now. So all of the events of your future timeline are foretold and currently exist in the space-time structure of the universe. It is not that the present moment is the only real moment, because to say it is the present moment is only relative to one frame of reference. As an example, when you're the observer who's traveling in the train and you see it as B is first and then A, relative to you, B is in the present and A lies out in the future. Because you haven't seen it yet, it'll be perceived second. In the other observer's case, A is happening in the present. A is happening in the present, and B happens in the future because they're closer to A and further from B. And so, in one perspective, an event that is seen as happening later is seen as happening before to another observer. And that just means that there's no objective ordering of the linear time sequence as you would have thought, according to the older Newtonian way of looking at time and space. So let me read then Einstein on this. And here's what he says about the second observer and all of that. He says, up to now, our considerations have been referred to a particular body of reference, which we have styled a railway embankment. We suppose a very long train traveling along the rails with constant velocity v in the direction indicated in figure 1, which is shown on page 456. People traveling in this train will use the train as a rigid body of reference, and they regard all events in reference to the train. So every event which takes place along the line also takes place at a particular point of the train. Also, the definition of simultaneity can be given relative to the train in exactly the same way as with respect to the embankment. As a natural consequence, the following question arises. Are two events, the two lightning strikes, which are simultaneous with reference to the railway embankment, also simultaneous relatively to the train? And we will show now directly that the answer is no. When we say that the lightning strokes A and B are simultaneous with respect to the embankment, we mean the rays of light emitted at the places A and B where the lightning occurs meet each other at the midpoint M of the length AB of the embankment. But the events A and B also correspond to positions A and B on the train. So let M prime be the midpoint of the distance A to B on the traveling train. Just when the flashes of lightning occur, this point, M prime, coincides with the point M. That was like my freeze frame kind of reference. But it moves towards the right in the diagram with the velocity v of the train. If an observer sitting in position M prime in the train did not possess velocity, then he would remain at M, and the light rays emitted by the flashes of lightning AB would reach him simultaneously. That is, they would meet where he is now situated. But in reality, he is hastening towards the beam of light coming from B, whilst he is riding on ahead of the beam of light coming from A. Hence, the observer will see the beam of light emitted from B earlier than he will see that emitted from A. Observers who take the railway train as their reference body must therefore come to the conclusion that the lightning flash B takes place earlier than the lightning flash A, and we therefore arrive at the important result. Events which are simultaneous with reference to the embankment are not simultaneous with respect to the train and vice versa. Every particular body has its own particular time. Unless we are told the reference body to which the statement of time refers, there is no meaning in a statement of the time of an event. Before the theory of relativity, it was always assumed in physics that the meaning of time had an absolute meaning, that it is independent of the state of motion of a body of reference. But now we have seen that this assumption is not compatible with the definition of simultaneity. Okay, so there you have it. In this simple thought experiment, Einstein is able to demonstrate that since light is the way in which we perceive objects in space, given our state of velocity relative to the light rays that are chasing our eyes, etc., we can see events happening in a different time sequence than others. It's so strange, right? When you guys look out, if you look into, say, a telescope out at the night sky, you probably have heard it said before that you're looking at objects as they were a long time ago, because it takes time for the light from whatever distant part of the universe to reach the telescope that's taking that light signal in. And so in some cases, like the Hubble Deep Field, you're looking at objects from the early universe because it has taken billions of light years for them to reach the receptacle of the telescope. So imagine this, right? As you look over to, I don't know, the telescopic image of a distant galaxy, you're looking at it as it seems to have been a long time ago because of the phenomenon I've described. But imagine now that there were observers in that part of the universe directing their telescopes back at us. Relative to them, they would be seeing us as objects that are in the past. So now I have a question: who's in the past and who's in the present? There's no objective answer to that. Relative to us, those are objects perceived from a distance that are way in the past. And on the other side of this example, they're seeing the same of us. This disabuses us of any notion that there's some objective sense of the present, past, and future. They're all equally located in space-time. And how strange is that? You would have thought that the past parts of you, being a little baby and a child, etc., they're just gone forever. And the future parts of you, they're just not yet there. There's no definite nature to them. They're yet to be. On the space-time conception, we have to grant, according to the theoretical results, the equal existence of all points within space-time, including this present, the past, and the future. So all those cheesy sayings about seize the moment, now is all that matters, there's no tomorrow, and the past is gone. According to Einstein's theory, this is all false. All the moments equally exist, and there's nothing special actually about the present. It's just as much an existing moment as a future and past and all the other parts of space-time. Well, there's a little more I want to tell you guys about the work of Einstein, so we'll develop this a bit more on Friday. But for the moment, try to read the article by Ted Sider. That's the next article that follows this in the book. And we'll just keep on talking about this stuff for a couple weeks. I'll assign new paper prompts, not next week, but in I think the following week. And this could be one of the optional topics. Epistemology could be one of the optional topics. And I think I'll add one more as well. But for now, guys, I guess let's break. Let me see if you're all right. And if you are all good with it, then I'll close the stream for now and just see you guys back in a couple days. So how's it going? Let me know. Okay, perfect. Thanks, Ryan, and everybody else. Really appreciate all your participation and hard work. So yeah, we'll check in on Friday. For the moment, if you need anything, do email me, and I'll be in touch. Okay, then. Take care, and bye-bye.